what we do today is a continuation of what we were doing, and we said in the previous class that an introduction to the ideas of quantum mechanics, particularly Pauli principle, remedies some of the problems that we encountered while fitting classical theory to experimental results. Now, as we said, the first thing that one tries to do in understanding a system of electrons which is basically which are fermions, is to treat them as a non-interacting quantum gas of quantum gas, and then calculate the properties of the electron gas from such a theory, and that theory is of course a quantum theory, and we wrote down the Schrodinger equation, the guiding equation for quantum mechanics equal to E psi. Now, in this equation, they look at the equation that we have not put any potential, that means the electron gas is still non-interacting as in our classical assumption, but the Newton's laws are now replaced by Schrodinger equation and the whatever comes with it, like Pauli principle and so on for a fermion. And then what we did was that we tried to identify the number of states. Basically, the state counting now becomes important, because not all values of momentum, so called momentum, k values, which we wrote down the solution of this as 1 by root over v e to the power I k dot r, and not all k values, not all k values allowed. Okay. Unlike in classical mechanics, where k can be a continuous variable, you can put from anywhere from 0 to infinity, and any k value is a possible k value. Then we identified that the momentum is h cross square k. This wave function gives you a momentum which is h cross k. The corresponding energy is similarly p square by twice m equal to h cross square k square by twice m. Now, the important thing was that we also said that the allowed k values will come from the boundary condition, and the boundary condition that we used was so called a periodic boundary condition called PBC, which essentially means in one dimension, for example, that you close the two ends of a line, basically identify 0 with L, so that it becomes a circle. Okay. And then consequently, we saw that the k values will be 2 n pi by L, where L n is an integer 0 plus minus 1 and so on and so on. So, that was the essential thing, and then we generalized it for 2 and then 3 dimension. So, the in 3 dimension, therefore, every volume 2 pi by L into 2 pi by L into 2 pi by L in k space contains one k allowed k value. So, that is 8 pi cube by L cube. So, this is the amount of volume in k space which gives you one k value that is allowed. Okay. So, on the basis of that, then we said that in a volume omega k in k space, we have omega k divided by 2 pi by L cube number of states, which is omega k times the volume in real space, L cube is the volume of the system by 8 pi cube. So, that was the state counting that we started doing, and we do it because at the end, at some point we have to sum over k for calculating all physical quantities, and then sum over k if you have to go over all the discrete values of k, then it becomes very difficult to sum. So, one looks for something which is like a region of k between k and k plus dk, over which how many states are allowed. So, one multiplies by that quantity, that phase space volume, and then one can even integrate. So, what we did was that we calculated certain physical quantities from this, and the value of the, for example, we calculated the number of levels. For example, remember electrons are fermions, spin half fermions. So, there are 2 states, 2 levels for each k value. So, when you put an electron in a particular k value, you are allowed to put one more electron with an opposite spin in certain your chosen direction of quantization in the same state. So, each k value actually accommodates 2 electrons. So, based on that we calculated several things. One of them is this number of levels n L, which is equal to number of electrons in the system, which was V by 3 pi square into k f cube. Now, k f is k h cross square k f square by twice m is E. So, k f is E f. So, f we defined was the Fermi energy. So, Fermi is momentum and E f is the Fermi energy. So, k f is root over 2 m E f by h cross square. So, that is how one calculates the number of electrons or number of levels in a system. See, number of levels is basically twice the number of k values, allowed k values. So, this basically gives you the total number of levels within a sphere of radius k f, or below an energy E f. So, that was something that we derived. We so we call that. So, we also derived the d n l d E equal to 3 by 2 n l by E, which is again the same as d n E electron number by d E equal to 3 by 2 n E by E. Okay. So, given all that, what we wanted to show was that we can actually calculate some physical quantities out of it. For example, we want to calculate the total energy, for example, up to the. So, what we do is we sum over h cross square k square by twice m all the way up to k less than equal to k f. Okay. Now, this gives you the number of k, you are summing over the momentum, the energy for a particular k value, and then summed over all those k values. But remember, at each k value, allowed k value, you can put 2 electrons. So, you have to multiply by 2. So, this is the energy of the electron in the solid, electronic energy that comes from the solid. So, and remember that again the for one allowed k value in a volume of 8 pi cube by L cube, which is the so 8 pi cube by V. So, in this volume in K space. Now, what we do is that we take so convert this any, for example, you are summing over a function of k, any function f of k, sum over k, you can write this as f of k into delta k by 2 pi cube by V. So, delta k is the volume in K space, and then dividing by this you get the number of k values in it, multiply f k by that number and then sum over k. So, that is the same as this. So, this is the this is basically an identity, and then what we do is that we take the limit delta k going to 0. Now, if this volume goes to 0, which happens when V goes to infinity, for example, so this delta k is a very small volume. So, we multiply that f k by that volume, that gives, and then by this quantity divide by this quantity, that gives me the number of k values there, and multiply f k, assuming that f k is not varying too much within that volume, because the volume is very small, and then this identity can now be converted to an integral. So, what we do is that now if you remember, it's basically f k delta k in this limit when delta k goes to 0 is nothing but integral of dk f of k. This is a very useful quantity, because now I have converted sum over all those discrete states which are allowed discrete states into an integral, and this integral, because the states are so densely packed, there are states at every 2 pi by L cube. So, every 8 pi cube by L cube. So, then and that number is extremely small. So, the total number of states in a region is very large. So, I can just convert this sum to an integral, okay. And that is very convenient, because I can now calculate the energy, for example, as an integral. So, that integral, so if that, remember that so I will okay. So, this integral is that means what I have done is that I have converted this f k into an integral, and then so I had, remember, into V by 2 pi cube here. So, I will put that in here, V by 2 pi cube. Okay. So, energy is now simply 2 times, so V remains 2 times dk. So, dk is okay, I will write it down again. dk by 8 pi cube h cross square k square by twice m. So, this is my expression for the energy. Remember, this 2 comes from the spin degeneracy, as I said, at each k value you will put 2 spins, and this was my sum. This is the sum for any function f k. I can write this f k d k as integral over this, and I had a multiplication by v by 2 pi cube. So, this v by 2 pi cube just sits outside, v by 2 pi whole cube. Okay. So, that is the expression. Now, I integrate it from 0 to k f, that will give me the total energy. So, how much is this? So, this is 2 v by 8 pi cube times, now this dk is basically 4 pi k square dk, and then I had this h cross square by twice m. So, I write the twice m here, 0 to k f into k square. So, this is equal to, this gives me 2 cancels, 4 pi gives me this 2 pi square, here v times h cross square into k to the power 4 dk 0 to k f. Okay. So, this is nothing but v h cross square by 2 pi square into 1 by 5 k to the power 5. There is an m here. So, I will put that k to the power 5 by m. So, this is v h cross square by pi square into k f to the power 5 by 10 m. This is the expression that you will find in many books, and this is a very convenient expression, because now I have expressed energy in terms of the total energy of the system in terms of its Fermi momentum and mass, and these are just constants. Then E by n, which is the energy per particle, energy density E by V, which is the energy density, is h cross square pi by pi square into k f to the power 5 by 10 m. Okay. So, once I have that, then I also had this expression that n, the total number of electrons, is k f cube into v by 3 pi square, and now I also have E equal to v h cross square by pi square into k f to the power 5 by 10 m. So, I just divide one by the other, and this gives me 3 by 10 h cross square k f square by m. Now, remember h cross square k f square by twice m is the E f. So, this is 3 by 5 E f. So, this is a very useful expression, because the energy per particle per electron is on an average is just 3 by 5 times the Fermi energy. This expression is very useful in calculating the energy of a system of particles, system of electrons. Now, one can even go further. just by looking at these expressions and a little bit of dimensional ideas, one can calculate several things. For example, let me just show you that how you can calculate for example, the pressure exerted by a degenerate Fermi gas, a gas of fermions like electrons in a solid. So, see, anything that is filled up to a particular region below Kf up to Kf, this is called a degenerate system of gas, because that is the name that stuck. This degenerate Fermi gas system exerts a pressure, because if you want to put in another particle in it, another fermion in it, you will not be able to do it at 0 temperature. So, all states are filled up, and so there is a pressure. So, if you want to compress it, if you want to change if you want to change the volume, then there will be these levels will come closer, and then you will have so there will be a reaction to that, and the system will, the degenerate Fermi gas will exert a pressure. So, so that pressure can be calculated. So, let us calculate the pressure from this degenerate Fermi gas. So, how do I calculate the pressure? Pressure is basically minus d dV, the fixed number of n. So, what you are trying to do is basically trying to change the volume of the system, and the system is opposing it. That is how that is the pressure that we are and why does it oppose it? Because there is a change in energy due to this change in volume. Okay. Now, let us start from here. See, this is, so let me just remove all the I will remove all the constants. So, 3 by 5 3 by 5 h cross square by twice m into, remember I had this expression for n. So, I am calculating the energy now. So, energy, this n I will replace from here. So, let me go ahead and do it, and then so this first let me calculate the so what I will do is I will replace Kf from here. So, let us do 3 pi square 3 pi square let us see n by V. Now, Kf is to the power 1/3 of this. Okay, so there is an n. This n is here to the power 1/3 times square. So, that is the, so this E, then from here E is, now you can see, is proportional to V to the power minus 2/3. So, I can write this as all the other things being constant, I can write this as, sorry, I can write this as V equal to some constant, say alpha V to the power minus 2/3. Now, I can go back here. So, what I do is that I calculate P equal to minus 2 by 3 alpha v to the power minus 2 by 3 minus 1, which is minus 2 by 3 alpha v to the power minus 2/3 divided by v, which is nothing but minus 2, minus is cancelled because there is a minus, there was a minus sign there. So, I have to put a plus sign here, plus 2/3 alpha v to the power minus 3 itself, this alpha v to the power minus 2/3 itself is E. So, 2 by 3 E by V. So, that is my P. Okay. So, 2/3 E by V is P. I can also calculate the bulk modulus, for example. So, bulk modulus is defined as B equal to minus V del P del V. Okay. So, this object, this is actually inverse of compressibility, K is the compressibility. Now, again I go back, I just derived the fact that P is some constant times V to the power minus 5 by 3. Okay. So, V to the power minus 3. So, all I have to do is to take a derivative of del P del V times minus V, which is minus, then becomes plus V times gamma V to the power minus 5 by 3 minus 1, okay, times 5 by 3. Again with the same argument that gamma v to the power minus 5 by 3 is so that v to the power minus 1 and this v will cancel. So, this will become simply 5 by 3 p. So, 5 by 3 p, let me 5 by 3 p is my bulk modulus. Equal to 1 by compressibility. Now, P again I can write as I just did, that P is 2/3 E by V. So, then B is equal to 5 by 3 into 2 by 3 E by V, which is 10 by 9 E by V. These are all relations that are useful when then again E by N is 3 by 5 E F, we just calculate in the previous page. So, that will give me B equal to 2 by 3 N by V into E F equal to 2 by 3 density of electrons times E F. N by V is the density. So, typically for a metal, typical metal, the bulk modulus for example is of the order of 10 to the power 10 to 10 to the power 12 dynes per centimeter square. Is fairly large, and so the idea of this whole algebra that we did, it is trivial straightforward algebra, is to get the physical quantities that you measure in your experiment, that you measure in experiments through some quantity which is actually measurable. So, I go to the last page. So, as you can see that bulk modulus is a measurable quantity. So, if I measure the bulk modulus, I can from and the density of electrons, I can actually get the Fermi energy, or vice versa. If I know the Fermi energy, if I know the density, then I can theoretically predict the bulk modulus and then do an experiment and check with the experimental values. So, these are basically free electron model, but using quantum mechanics, and that quantum mechanics puts a lot of restriction on the electron system, because you can't put two electrons in the same state. More in the same value you can put 2 electrons, because there is a spin, but that means that there is a severe restriction on the number of electrons per state. It cannot be more than 2 per k. So, that means you are going up in energy while filling up the states. So, your ground state already has quite a large amount of energy, which we found out that it is typically 3 by 5 average energy per particle is 3 by 5 EF. EF is quite a large quantity, it is between 1 to 10, 15 electron volts in certain system, and that means that you had to pay that much of energy even in the ground state to construct the ground state of the degenerate electron gas, which is filled up to the Fermi level, and consequently all the physical quantities like bulk modulus, compressibility and so on, pressure can be worked out from such. So, in the next class what we will try to do is to show the effect of this Pauli principle when you want to supply some energy into the electron gas, degenerate electron gas, and specific heat, for example, can be calculated, and the right temperature dependencies come out of this specific heat from this kind of a calculation, which originally was done by Sommerfeld. Thank you.